Hello, my name is Fisher Tyson. I'm a student currently at UNCW, and right now I'm going to present my findings for the course I've been taking at Duke University Engineering. I have chosen Python for this demonstration. The goal is to calculate the predicted output of a nuclear power plant by using the features listed in the data set that have been provided. Now, using these features, we can evaluate how we want to model this by using two separate forms of an algorithm. This would be linear regression and then a random tree in order to calculate through which one is going to be the most successful in providing the most accurate data. Now, going in, we import into Python, calculate the results of over 9,500 hourly readings, a lot of data, and definitely requires selections of those data in order to get the best result possible. Going into our approach, use the features like ambient temperature, ambient pressure, and then the relative humidity, and also the amount of exhaust pressure that's leaving. Now, with linear regression, we can see how this can be highly interpretable, but does not give us the best, incorporated evaluation, as we'll see in my results from determining the differences between the two. In random forest, and that we are able to chunk out selections of the vast majority of data and be able to use that to have a more definitive answer that can be interpretable and understandable, and we can backtrack to how we got to there in this machine learning. I want to go towards how we wanted to target towards meeting that R squared value that is closest to 1, because that is the main determining factor in choosing which data set I'm going to use in order to evaluate into the test set, because 80% of this is done during the training period. And that's so that we can have a more predictive process for the testing. Now, tuning that random forest definitely worked a lot better than using just a general model from a random forest generation, as the different features can be weighed. I can show you in the code where it has been weighed. We add those weights in about a k-fold of 5 different factors. Now, the total of these weights adds to 1, but varying the amount that each has influence on the result can show how we can find a better result. As you can see, the tuned showed the lowest amount of like model comparison compared to just the normal random forest, and compared to linear regression, which is going to have the least valuable result in concerns to this evaluation, will land us in finding the total hour power output in our desired outcome. So our output would need to use the random forest that has been tuned towards those weights. Now, in the final evaluation, we have 3 graphs here that show how this scatter plot can reach that desired R2 value. And although it's not completely perfect, and none of these machine learning um, like systems will ever equate to just 1, but it's very close at 9 or 0.964. It's very close to where we meet that desired R squared value. Now, in selecting our feature importance, ambient temperature was definitely the most important in varying our desired energy output. Now, even thinking about this rationally, when you are in a nuclear power plant, the desired goal of nuclear fission is to generate heat for steam to create that volumetric pressure to spin turbines and eventually generate electricity. So if we increase the heat, there are some safety concerns on whether or not this could lead to a nuclear meltdown, especially with the exceeding uses of data centers and the need for energy output in the United States. I think there's talks about plans in Utah to where one would outseed 10 times what uh, Paris uses in their concurrent usage of energy. So definitely high dependency on the ambient temperature, so that way we can produce energy. So in summary, decided to use the a random decision tree matrix in order to equate the result that would leave us the maximized energy output in this power plant. using the data provided from the Excel document that has been inputted into Python and used for further evaluation.